Okay, so hello everyone, thank you for being here. So today we have the pleasure to welcome Pierre-Yves Duerinck, who is a PhD student at IPHC Strasbourg and University of Brussels. He's in the third year of PhD, and he will present the results he got from the two first years of his PhD. So Pierre-Yves, whatever you want.
Okay, thank you very much. Thank you for the introduction. And thank you for organizing this webinar and giving me the opportunity to present my work here. So as you said, my name is Pierre-Yves Duerinck, and I'm a PhD student in both Brussels and Strasbourg universities. And today I will talk about the ab initio description of antiproton-deuteron hydrogenic states and discuss the result I obtained with my collaborator, Jeremy Doerr-Ali, Rimantas Lazauskas, and Jaume Carbonel. So during this presentation, I will first give a brief overview about low energy antiproton physics and talk about the nucleon-antinucleon, so NN bar interaction. I will then detail the formalism I use for my calculation and finally discuss my results. So first of all, the interest for low energy antiproton physics has been developed, namely at CERN, with first the low energy antiproton ring, LIR, that you can see here, and that has been shut down in 1996. And this interest has been revived with AD, the antiproton decelerator, and ELENA, the extra low energy antiproton ring that you can see here. So these facilities provide low energy antiproton beams that can be used for various kinds of experiments to study the properties of antimatter, but also exotic system in which particle and antiparticles are bound together, or even standard matter to some extent. Here I give you some of the experiments that take place at CERN, for instance, Bayes experiments, which study and compares the properties of proton and antiproton. Alpha, which does basically the same with hydrogen and antihydrogen. G-bar and AGIS that studies the effect of gravitation on antimatter, and Asakusa that mainly do antiprotonic helium spectroscopy. The experiment I'm interested in, and that is the main motivation for my theoretical calculation, is PUMA. So PUMA stands for Antiproton Unstable Matter Annihilation. And this experiment aims to study the nucleus skin densities of short-lived nuclear isotope produced by ISOLD using low-energy antiproton as a probe. But the idea of the experiment is that an antiproton can be captured by an ion or an atom to form this kind of antiproton-nucleus system in which it will eventually annihilate with a nucleon. And the idea is that the annihilation process takes place in the periphery of the nucleus, so that by measuring the ratio between the number of antiproton annihilated with proton and the number of antiproton annihilated with neutron, data can be inferred about the tail of the nuclear density. So while a qualitative picture of what will happen in PUMA experiments is known, fully microscopic treatment of this kind of system remains to be developed, and several questions remain unanswered. For instance, how can we interpret the data from theoretical prediction, if we can provide any? Also, different questions related to the validity of existing NN-bar models and the associated model dependence. So to try to provide an answer to this question, my job and my PhD main aim is to provide a microscopic treatment of light antiproton nucleus system. If we take a look at CERN accelerator complex for these experiments, so the antiprotons are produced from a high energy proton beam that comes from the proton synchrotron here. So the protons are smashed on a thin iridium target, which produce lots of antiproton. And these antiprotons are then directed into the antiproton decelerator and further decelerated by ELENA. So here you have an overview of the ELENA facility. So from the antiproton beam produced by the antiproton decelerator, ELENA will reduce their energy up to an energy of about 100 keV. And LNA can also produce different bunches so that LNA can serve different experiments at the same time in antiproton beams. So here you have the experiment I told you about, and here you have PUMA that has its own beamline. So the idea of PUMA experiment is then to store these antiproton in a magnetic trap and then to transport this trap to ISOT using a truck in order for the interaction with radioactive nuclei to take place. So here you have a sketch of the itinerary that will follow the antiproton about 2 kilometers, and that is estimated to last 1 to 2 hours. If we take a closer look at what happened inside of this magnetic trap and what happened when a low energy antiproton interact with an atom or an ion, well, this antiproton can be captured by an atom. So it will basically replace one of the electrons, and it is captured on a highly excited Coulomb orbital to form a quasi-bound state. Quasi-bound system, so a state with a complex energy. It has a given width since it is unstable, and the real part of the energy is more or less given by the binding energy of the nucleus plus the energy of a Rydberg state. Then the antiproton will decay via either X-ray cascade or Auger electron emission. And finally, when it reaches a lower state and feel the influence of nuclear forces, it will annihilate with a nucleon. And this is this last step that I consider for my calculation. So the idea is to have a non-relativistic description of this kind of system by solving the few-body-Schrodinger equation here and perform ab initio calculation for the simplest cases, so 3 and 4-body system. And in this case, each nucleon of the nucleus is treated explicitly. This problem is actually quite complex for two main reasons. The first one is the presence of the poorly known N-bar interaction and the associated complex annihilation dynamics. The second one is the presence of different scales. So these states, these hydrogenic states, are governed at long range by the Coulomb interaction, which means that their wave function is spatially extended. But on the other side, we also have to capture very fine effects that are related to the N-bar interaction, and accounting for both of them at the same time is quite challenging from a numerical point of view. So to perform ab initio calculation, I need interaction, a potential for both NN and NN-bar pairs, and this is what I will discuss now. So most of what we know about the nucleon-antinucleon interaction comes from Lear's data and Lear's experiment, and mostly nucleon-antinucleon scattering. If we take, for instance, the case of proton-antiproton scattering, it involves different processes, for instance, the elastic scattering, but also the charge exchange process, which is the formation of a neutron-antineutron pair, and the annihilation into a large variety of meson channels. On this figure, you have the cross-section associated with each of these processes with respect to the momentum in lab frame and computed with different existing model. And you can see that at low energy, which is my interest, the annihilation cross-section is more or less twice the elastic cross-section, which is larger than the charge exchange process. This means that at low energy, clearly you cannot neglect the annihilation since it is the dominant process, so you have to include it in your calculation. Another source of data for the N-bar interaction is protonium. So if we neglect the strong nuclear interaction between a proton and an antiproton, we would have the formation of an hydrogenic state. So a hydrogen-like state with an energy given here. So it's the energy of an hydrogen state with a different Rydberg constant. So here the Rydberg constant is about 12.5 keV. And the associated Bohr radius is about 60 femtometers, so it's 1,000 times smaller than an hydrogen atom. However, due to the nuclear interaction, these hydrogenic levels are shifted, so they gain a given width because they are unstable. And this shift between the actual energy and the hydrogenic energy can be computed and has been measured for low-lying state using by different experiment. So plutonium is a privileged system to test an N-bar interaction at low energy, since it only involves a nucleon and an antinucleon. And since plutonium, lots of heavier antiprotonic atoms have been studied. However, from this heavier system, it is hard to extract useful information in order to build an N-bar models. So here you have the hydrogen-like spectrum of plutonium. So it's really the same as an hydrogen atom, just with a different energy scale. And if you look in more detail for instance, 1s and 2p states, well, you have a fine structure that can appear. So this fine structure is due to the different quantum numbers of spin and total angular momentum. And they have a different energy from this hydrogenic level 1s due to the nuclear interactions. And so what we aim to compute is this shift, so the real part of the shift and the associated width. So for S states, we have two different states depending on spin. And the order of magnitude for the shift is KV. For a P state, we have 4 of them here, and the order of magnitude for the shift is milli-electron volts, and for D wave is micro-electron volts, so it's really a fine structure effect, and as L increases, this effect becomes smaller and smaller. So the way we can formulate a nucleon-antinucleon interaction from a theoretical point of view is actually to start from the nucleon-nucleon interaction, which is better known. And the traditional way of formulating an interaction is the meson exchange theory, in which the potential is expressed as the sum of different terms, and each term is associated with the exchange of a specific meson. For instance, we have pi and here for the tail of the potential, heavier mesons such as theta, rho, or omega, and possibly fictional one depending on the model. So this is quite the old-fashioned way of formulating an interaction. It is, however, yet efficient and still widely used in nuclear calculation. So the associated NN bar interaction is obtained from a G-parity transform. So each of these meson has a G-parity, which is plus or minus 1, and it is shown that we can obtain the NN bar potential from the NN potential by reversing the sign of negative G-parity meson term. By doing this, all the features that were strongly repulsive at short distances become strongly attractive, which means that with this kind of potential, we expect deep bound and resonance states. So these states are theoretically expected, but have never been experimentally measured. And one of Lear's main goal was to measure this state actually. So this only provides a part of the NN bar potential, since here we do not account for annihilation yet. To account for annihilation, we need to introduce phenomenology. And to give a more complete picture about an N-bar system, there is also a more recent formulation that is based on chiral effective field theory, which is, let's say, the modern way of formulating the NN interaction from QCD forces. And it is, for instance, the case of the Duerinck potential that I will discuss later. So concerning the annihilation, well, as I told you, it's a quite complex process, and it involves lots of meson-producing channels, mainly involving pions. Here I give you different examples for proton-antiproton and neutron-antiproton annihilation, and you can see that you have lots of possibilities with typically much more than 2 pions actually. And these channels are actually quite hardly included in ab initio calculation. For this reason, we only explicitly consider the NN bar channel here and here. While all these meson channels, they are treated using phenomenological models. And the traditional way of accounting for the annihilation is to use optical potential. So the idea here is to add a complex term to the potential, And the role of the imaginary part of the potential is to induce a loss of probability current in NN-bar channel in order to simulate the effect of all annihilation channels at the same time. The form of this term is arbitrary and usually chosen as a Wood-Saxon potential like this, with parameters that are adjusted to fit experimental data. In this table, I give you different optical potential and their respective parameter, so Duerinck-1, Duerinck-2, and Konowaise potential. If you look at the amplitude of the Wood-Saxon wave, for instance, it is given in GeV. So here you have 20 GeV, here 500 MeV, and here 1 GeV, which is really significant in regard to the rest of the NN-bar interaction, and highlight the importance of the annihilation process in NN-bar system. So in some cases, you have both a real and an imaginary part. It is the case of the Duerinck potentials. For Konowaise, you only have an imaginary part for the Wood-Saxon part. Concerning the range of this Wood-Saxon well, here there is nothing unusual. It's just related to the range of the nuclear interaction. So despite their simplicity and limited dynamics, since this term is the same for all partial waves, optical potential are quite successful in reproducing experimental data. And if you carry out scattering calculation with this kind of potential, you have non-unitary S matrices, because due to the imaginary part of the potential, a part of your probability flux is suppressed and it's just lost actually, it goes nowhere, it's just suppressed from the system. So different optical potentials have been developed through the years. And what we can say about this model is that they all roughly reproduce low energy observable and integrated cross-section and provide a reasonable agreement with experimental data. So here, for instance, you have the S-wave level shift of protonium calculated with different optical potential, Duerinck-1, Duerinck-2, Konowaise, Paris potential, and Duerinck. And if you look at both the real and imaginary part of the level shift, you can see that these values are all quite similar and give a quite good agreement with experimental data for both 1S0 and 3SD1. Concerning P wave, if you look at 1P wave, 1P1 wave, it is quite the same conclusion. It's quite similar for all models. For 3P0, however, we can notice different differences that occur. For instance, if you take the value here predicted by the Ulick potential, it is quite different from the other optical potential. And if you look at experimental data, they are all quite different. So even for two-body system, we have some kind of model dependence that occur that is due to our limited knowledge about NN-bar interaction. So concerning the integrated cross-section, they comes from the coherent sum of different partial waves and are quite similar from one model to another. However, if you compare for each partial wave the phase shift, for instance, which has been made in this paper, while they reported that large and systematic differences have been observed in almost all the partial waves. So there is model dependence that occur for protonium, for two-body system already, and that is due to our limited knowledge of an N-bar interaction. So another possibility to account for the annihilation process is the coupled channel model. So here the potential is real and the annihilation is simulated by the addition of effective meson-anti-meson channels, so MM-bar channel, that will mimic the production of the real meson. So this approach is still phenomenological, but it provides a more realistic description of the annihilation process, since here the flux that is taken out NN-bar channel is redistributed into this MM-bar channel, which means that we have in this case a unitary S matrix, and also it automatically includes the possibility of reconversion from MM-bar to NN-bar, which does not exist for optical potential. So in my work, I constructed a couple channel potential with the following channel here, where each NN bar channel is coupled to a MM bar channel via short-range Yukawa potential. And I adjusted the parameter of this meson and the parameter of my potential in order to fit the low energy observable obtained with an optical potential, which is the Konowaise model. The idea of doing this is to have two phase equivalent potentials, so two potentials that provide the same low energy observable, but that have a very different implementation of the annihilation process, and to see if we transpose them into a three-body system, if we observe a strong model dependence or not. So to highlight this difference in terms of annihilation dynamics, on this figure, you have plotted the annihilation density that are related to the probability of annihilation with respect to proton-antiproton distance. So in red, you have the annihilation density with Konowaise, and in blue with the couple channel model. And you can see that it is strongly related to the wave function. So the wave function are quite different, which means that annihilation density are also quite different. For Konowaise, we have a broad peak here, while for the couple channel model, the peak is narrower and slightly shifted to the left. So now the idea is to investigate the model dependence in a three-body system. This three-body system is the antiproton-deuteron system, and to see if with all these couple channel and optical potential, we observe strong differences or not. So in order to study the antiproton-deuteron system, we need to solve the Faddeev, the three-body Schrodinger equation. And to do that, I'm solving Faddeev equation in configuration space. So the idea of Faddeev formalism is to split the wave function, the three-body wave function, in three components called Faddeev components. And these components are associated with a 2+1 partition of the system. So we have three of them. And we can show that Faddeev components are a solution of the Faddeev equation that I give here. So there are three of them. And if you sum all your Faddeev equation, you recover the full three-body Schrodinger equation. So these approaches are strictly equivalent. Concerning this equation, it is interesting to notice that one Faddeev component is coupled with the two other on the right-hand side by a potential term here. And if this term is a short-range term, we can show that Faddeev equations are asymptotically decoupled, which means that I have a region of space when only one Faddeev component is non-zero. And this means that for each of them, I can impose an independent boundary condition. And this is why Faddeev formalism is very suited to handle few-body scattering problems. In my case, however, I have to account for the Coulomb interaction, which is long range, between the proton and the antiproton, which means that I need to introduce some correction to the Faddeev equation in order for my statement to remain true and to obtain numerically stable results. So these corrections have been introduced by Merkuriev, and so to ensure this asymptotic decoupling of the Faddeev components, the idea is to split the Coulomb potential in two parts, a short-range part and a long-range part, by the means of a cutoff function. And the aim is to keep this coupling on the right-hand side, the coupling with the other Faddeev components by short-range potential. The price of doing this is to account for some long-range contribution on the left-hand side of the Faddeev equation. But by solving this Faddeev-Merkuriev equation, I'm sure to obtain numerically stable result in a problem in which the Coulomb potential is present. From a numerical point of view, the resolution is made by a partial wave expansion. So each Faddeev component is expressed as a partial wave theory with the coupling of specific orbital momenta and spin, so the quantum numbers, and the definition of a radial wave function for each partial wave. These radial wave functions are then expressed as a linear combination of square integrable function. In my case, I consider Lagrange-Laguerre function, which are basically polynomial multiplied by exponential function. So these functions have very good properties, and namely for calculating the matrix elements of potential in interaction term, and they have also good behavior close to the origin. So at the end of the day, my only unknown are these C coefficients here. So I transpose my Faddeev equation into a linear algebra problem. And so I can compute this coefficient together with the energy by solving an eigenvalue problem for bound states. And for scattering states, since the energy is known, I solve linear system. So the matrices involved are, of course, of very large dimension, which means that I have to rely on iterative method to solve these problems and use methods such as Power method or Lang's algorithm to solve the eigenvalue problem, or for linear system, we have GMRES or BCG stub. So if we take a closer look now at our antiproton-deuteron system, what kind of Faddeev equation can we define for this problem? Well, we can start with our three Faddeev component here that comes from the cyclic permutation of p, n, and p bar particles. And here I have the pp bar interaction, which is coupled by charge exchange through NN bar channels. So due to this term here, I have a new particle channels, and I have to add three additional Faddeev component. And so this is the rule. For each additional particle channel, I need to add three additional Faddeev component. So for optical potential, I have 6 Faddeev components, so 6 Faddeev equation that can be reduced to 5, thanks to the symmetry of the wave function. For the coupled channel model, the idea is the same. I still have these 6 Faddeev components that comes from the initial channel and charge exchange. But within the coupled channel framework, each NN bar channel is coupled to MM bar channel, which means that here I have PP bar, NN bar, and NP bar. I need to add 3 additional meson channels, so 9 additional Faddeev components. So in total, I have 15 Faddeev components, so 15 Faddeev equation. This can be reduced to 8 by exploiting the symmetry of the wave function and by considering that the meson do not interact with each other. So if you compare the coupled channel and optical potential, the coupled channel potential is heavier from a numerical point of view because we have more components and more equation. And there is another layer of complexity that arises from these meson components, because since I consider that the meson do not interact with each other, in all of these Faddeev components, I have the three-body breakup. So I have an exponentially diverging wave function here, which is hardly described using square integrable function. And so to overcome this problem, I can solve the Faddeev equation in conjunction with the complex scaling method. And the complex scaling will basically kill this exponentially diverging behavior in all these breakup wave functions and provide a simpler resolution of my three-body problem. So now we can look at the result I obtained. So the first thing I studied is the zero energy antiproton-deuteron collision and the calculation of the scattering length with the complex scaling method for the coupled channel potential. So in this table, you have the scattering length computed for different three-body states, so 2 S state and 1 P state. So here is the total angular momentum. And you have different NN plus NN bar interaction. For the NN part, we have Malfitentian potential, which is a central potential, and argon G18, which is a realistic potential. While on the NN bar part, we have Konowaise, so this is an optical model, and coupled channel, which is the coupled channel potential. So if you look on a given line, you can see that all these results are quite close to each other, which means that we have a small dependence on both nucleon-nucleon and nucleon-antinucleon interaction, which is a good news here. And this also means that despite the fact that the implementation of the annihilation is very different, so the theoretical background of Konowaise and CC model are very different, we can nevertheless obtain a good agreement within a few percent of differences. So we can also compute and study the level shift of dp bar system. So here the idea and the story is the same as for protonium. So if we neglect the strong nuclear interaction between the deuteron and the antiproton, we would have formation of an infinite set of Rydberg states, so heterogenic state, with an energy that is given by the binding energy of the nucleus plus the energy of a Rydberg state. Here, the Rydberg constant is about 17 keV. However, due to the nuclear interaction, these hydrogenic levels, they are shifted and broadened so that the actual energy is a complex quantity given here. And what we can compute is the shift, so the difference between these two quantities. This shift can be calculated in two ways. So the first one is to compute the eigenvalue of the complex Hamiltonian. So this approach is quite challenging because of the presence of these two scales. The wave function of this hydrogenic state is spatially extended, so I need a discretization grid that is spatially extended. However, on the other side, I need a very fine grid because I have very fine effects that are related to the short range NN bar interaction. So this, from a numerical point of view, is quite heavy. An alternative approach that has been explored is the use of Truman relation. So Truman relation provides a direct link between energy shift and scattering length and is initially formulated for two-body system. Here we would like to see if this can be applied to hydrogenic three-body system. So for instance, here you have the Truman relation for an S wave, where it is quite easy. Actually, you just have a proportionality relation between the scattering length A0 and the level shift. So in this table, I compare the two approaches for the same states and the same interaction as before. So here you have two columns. On the left-hand side, you have the energy shift computed from the eigenvalue of the Hamiltonian. And on the right-hand side, you have the energy shift computed from Truman relation. And if you compare the value for each column of each interaction in each state, for S states, results are really close to each other. For P wave, dispersion is slightly larger, but we have quite nice agreement between these two methods, however, which means that Truman relation is a consistent approach to compute the level shift. And since the calculation of the scattering length is far less demanding than the calculation of the eigenvalue, this is a very interesting approach to study heavier systems. So we can also compare the result obtained with different optical potential. So here again, you have the same state and the same NN interaction. And here you have the result computed with different optical potential. So again, the HR1, the HR2, Konowaise, and Duerinck potential. If you look on a given column for all these potential, we recover the small dependence on the NN interaction. And for S wave, if you look on a given line this time, so you compare different NN bar models, for S wave, we have a nice agreement between all these models. And for P wave, however, the situation is slightly worse because we have already a larger dispersion. For instance, if you compare the result obtained with Konowaise and Duerinck, we have 20 MeV of difference, while between Dover-Richard potentials and Konowaise, we have almost a factor 2. However, in all cases, the imaginary part of the shift remain more or less the same. So here is the first indication of that model dependence can occur on a triple-D level, as it is the case for the P wave of protonium. Here you have on this figure a summary of the result for the S wave level shift. So for you have here the spin average S wave level shift for antiproton-deuteron system. On black, you have different experiments. So here you have an experiment with the arrow bar for both the real part of the shift and the imaginary part. And here the dashed line are the error bar of another experiment that only provided a value for the imaginary part of the energy. The full dots here are the result I obtained with different optical potentials. So again, the HR1, 2, Konawayse, and Duerinck, while the other point here are results previously published in literature by Lata and Wischek. And so here, our results are really exact solution of the three-body problem in the numerical sense. So we could expect a nice agreement with experimental data. So we have a nice agreement between all these models for the real part of the energy, especially where it is really close to 2 keV. However, if you look with respect to experimental data, we have strong discrepancies for the real part of the energy. We have almost 4 sigma discrepancy, which means that there is something unknown in this n-bar interaction that do not allow us to have a good agreement between experiments and theory. Concerning the imaginary part of the energy, well, the error bars are quite large and all the models lies within these error bars. So up to now, I only considered the states, so spin uncoupled states, so three-body states in which I have only one asymptotic channels, but there are also three-body states such as P1 and P3 in which we have two of them, so the same value of L, but different value of J. And the complexity due to this term is that because of the fact that deuteron has a non-spherical distribution, it has a non-zero quadrupole moment. And because of that, these asymptotic channels, they are coupled together by long-range terms that decrease as 1 over r cubed. And these are several implications. The first one is that I cannot directly use Truman relation for this state because Truman relation is formulated for the scattering by a potential in 1 over r and not 1 over r cubed. And also, if you compare the level shift computed with central and realistic NN interaction with the same NN bar interaction, we have strong differences that appear. For instance, for Malfittention potential, well, Malfittention is a central potential, so we don't have any quadrupole moment in deuteron wave function. So this shift is only due to the NN bar interaction, while for argon V18, so it is a realistic potential, so it has a non-zero D component for the deuteron wave function, so it has a non-zero quadrupole moment, and the shift that is computed here with respect to the pure hydrogenic state include the contribution both of quadrupole moment and nuclear interaction. And so for this comparison to be relevant, we would need to disentangle these two effects. So finally, we can compare the shift computed with different NN bar potential for this coupled P state. And here, while we had a nice agreement for S wave, we have found sizable differences in this P wave. So as it is the case in protonium, for instance, here, if we compare the result obtained with Konawayse potential and Duerinck, here for the real part of the energy, we have indifference even in sign. Also the case here. Here we have a factor 2 between the real part of the energies, and here a factor 3. So in a three-body problem, as it is the case for protonium, we observe strong model dependence, and this model dependence is due to our limited knowledge about NN bar data, NN bar interaction. So due to the limited amount of experimental data, we are not able to sufficiently constrain the parameter of this NN bar model in order to have coherent results with all these models. Well, finally, we can compute the antiproton-deuteron annihilation density. So as I told you, annihilation density is related to the probability of annihilation of the antiproton with respect to its distance with deuteron here. And this quantity is actually interesting to compute in regard to PUMA experiments. So PUMA experiments make the hypothesis that the annihilation mostly takes place in the periphery of the nucleus, which means that by comparing this annihilation density with the deuteron nuclear density, we can see if this hypothesis makes sense or not. So for instance, here you have the annihilation densities calculated with coupled channel and Konowaise model for an S wave on the left-hand side and with a P wave on the right-hand side. So for the S wave, so the coupled channel and Konowaise curve are slightly shifted with each other. However, the conclusion is the same. Since the annihilation density decreases faster than deuteron density, it means that a substantial amount of the annihilation takes place inside of the nucleus. So here we do not expect a peripheral annihilation. While for a p state, the annihilation densities are more lookalike and scales nicely with deuteron density decay, which means that in this case, we expect that the antiprotons are mostly annihilated in the periphery of the deuteron density. So in this annihilation density support this hypothesis made by PUMA experiment. So time for the conclusion. So in my work, I investigated the model dependence in a three-body problem, which is the antiproton-deuteron system, by comparing different models, so different NN-bar models, optical and copper channel models. Concerning the calculation of the level shift, we observed a small dependence on both nucleon-nucleon and nucleon-antinucleon interaction for the S wave. But we also observe strong model dependence in some P wave, which means that our understanding of the NN-bar interaction can still be greatly improved. Also, despite their very different dynamic, we found that optical and coupled channel potential provide similar results, which highlight the interest for optical models given their relative simplicity of use. And we also shown that Truman relation is a consistent approach in order to compute the level shift of uncoupled state here. And that is a promising approach for heavier system. Concerning the annihilation density, we shown that the annihilation is expected to be peripheral, at least for P wave and higher wave actually, which supports the major hypothesis of PUMA experiment. And as prospect and ongoing work, I plan to study this term in 1/r cube in dp bar system in order to generalize the use of this Truman formula to all possible states. And I'm currently performing a four-body calculation by solving the Faddeev-Jakubowski equation, which is the generalization of Faddeev equation to four-body system, and compute the level shift of antiproton plus H3 and antiproton plus helium-3 system. Okay, thank you very much for your attention.